Sorry, this class is late now. Okay, am I audible?
Yes, sir.
Yes.
Okay, so now we can start. So in last class we were on the del operation of the vector quantities. Okay, so we have studied the different del operators, the operations. So del is a vector quantity. Del itself is a vector quantity. It represents del I. It can be written as del I del xi. Okay, it is a vector quantity. Okay, so there are different type of operations which can be occur with the del operator. So first is del operation on scalar. This is a mathematical part which we will use during the application. Okay, so this is not the actual subject. You know, syllabus will start after in next week or the after 15 or 20 August. Okay, actual syllabus. This is the mathematical part which you should know before going before starting the actual course. Okay, so del operation of s. S is a scalar quantity. It can be written as del s by del x1 del 1 plus del s by del x2 del 2 plus del s by del x3 del 3. Okay, this is for the scalar quantities. Now the vector quantities, you have the different operations. First is gradient of a vector field. It is a dyadic product. So del V, gradient of a vector field, it can be written as del I del by del xi del j. These are the unit vectors. Vj is the magnitude of the velocity. It can be written as del I del j del vi del vj divided by del xi. So this is a second order tensor quantity. Okay. Now second is the divergence of a vector field. It is a dot product. Okay. Second is divergence of a vector field. It is a dot product between the del operator and a vector quantity. So this quantity can be written as del I del by del xi dot del j vj. So the magnitude will be multiplied del vj divided by del xi, and you have to take the dot product between these two unit vectors del I dot del j. So when you take the dot product between these two unit vectors, this product will become del vj divided by del xi. It becomes the conical delta del ij. Okay, and del ij equal to 1 when I equal to j. Otherwise, it is a 0. Okay, so you have to replace I to j. This will become del vi divided by del xi. Here I is a dummy indice. There is a summation sign for I. So it can take the value 1, 2, 3 for the three-dimensional space. So you have the dv1 by dx1 plus dv2 by dx2 plus dv3 by dx3. Okay. Now third is the curl of a vector field. Curl is a cross product between the a del operator and a vector quantity. Okay, so you can write del cross V. This will become del I del by del xi cross del j multiply by Vj. So magnitude will be multiplied. Del Vj divided by del xi. Now you have to take the cross product between del I cross del j. These are the unit vectors. So when you take the cross product between these two unit vectors, you will get del xi. Alternating unit tensor epsilon I j a new indices k multiplied by del k. Okay, so you have this term here. I, j, and k, all three are the I, j, and k, all three are the dummy indices. So you have the three summation signs. Okay, this is the curl of a vector field. Now again, then next is the operation is the Laplacian of a scalar field. That is 4. Is called so Laplacian of a scalar field is defined as del dot del s, where s is a scalar quantity. You will find this operation during the heat transfer when we study the transportation of the when we study the how the temperature varies across the during the convection field. Okay, so during the convection you will find this term. Okay, because temperature is also a scalar quantity. So Laplacian of a scalar field you will find during the temperature. Okay, so this can be written as del dot del s. This can be written as del I d by dxi dot del j d by dxj multiplied by s. S is a scalar quantity. Now this term again the magnitude will be multiplied del by del xi del by del xj s. Now you have to take the dot product between del I and del j. So when you take the dot product between the del I and del j, you will get yes. Any
So
question?
del ij.
Del ij. Xj. Chronicle delta ij. This will be plus 1 when I equal to j. So you will get here you have to replace I equal to j. 1 minute.
Sir, you are on mute.
So basically, you have to replace the. Am I audible?
Yes, sir.
Yes,
You have to
sir.
Yes, sir.
replace the I to j. When you replace the I to j, the Laplacian coefficient will become del square s del xi square है ना, because here I comes twice, I1 I del xi multiplied by del xi, so it is a dummy indices. Again you have the summation sign for the I. Okay, or in the short form you can write this like, it can also written as, in different books you will find this expression. This is also the Laplacian of the scalar field. Okay, del square s, that is same thing. Okay, you also have the Laplacian of a vector field. So what is the Laplacian of a vector field? It is represented by del square V, or you can say it is represented by del dot del V. Okay, so if you take this, so this will be like, if you solve this problem, this will comes like this: del dot del V. Here you have the del operator. It is written as del by del xi unit vector del I multiplied by del xi dot unit vector del j del xj and unit vector del k vk. Okay. Now you have to take the diatic product between the j and k. And here there is a no sign. So this is the diatic product. So you will get del I del by del xi dot del j del k multiplied by del vk divided by del x j. Okay, you have to remember one thing: whenever you have the second order tensor, and I will come on the second order tensor, but here again first, because this is a second order tensor, that's why I have to explain this. So when you have the second order tensor, any operation between the second order tensor, the first operation will done between the unit vectors which are near to each other. Okay, here you have to do the dot operation. So dot operation will only done between the two unit vectors which are near to each other. So I and j are the near to each other. Okay, you cannot do the dot operation between I and k. And now you have to do the dot operation between the I and j. And the magnitude, this magnitude will be multiplied. So del by del xi del vk divided by del xj, and again you have the dot operation between del I dot del j del k. Okay, so this dot operation will occur between del I and del j only. Okay, here you have to replace it by the conical delta. It will become del ij, that will be equal to 1 when you have I equal to j, and then you have the del k. So this equation is equal to, here I am replacing j to I, del square by del xi square vk multiplied by del k. So that can be written as del square v. Okay, so this is a vector quantity. Okay, Laplacian of a vector field is a vector quantity. So these expressions have the these operations have the very specific use in the physics as well as in the chemical engineering. When you derive the expression, when you derive the mathematical model for transportation, then you will find this type of expressions. Okay, even if you search on internet and just in Google you type Laplacian of a vector field. Okay. And if you find the curve, है ना, then you will find very specific curves for the Laplacian. Okay. These type of curves. These curves represent the Laplacian. If you search the curl of a vector field, this is the curl of a vector field. So these lines shows the curl of a vector field. Okay. Similarly, the gradient of a vector field or the divergence of a vector field. So this type of curve, this is the divergence of a vector field. So basically, this in the physics and in the transport phenomena, how the material transported from one point to other point. So that will be represented by the these expression, these mathematical expressions. Okay, so that's why these are the very important expressions. Okay, now now we will see the operation between the operation between the second order tensors quantity, mathematical operation between the second order tensor quantities. Mathematical operations between second order tensor quantities. Okay. Suppose you have a tensor quantity tau and sigma. Both are the tensor quantities. In first class, I have already told you tensor quantities are represented by the Greek letters. Okay. So if you have the Greek letter and there is a sign between below the Greek letter, that means it is a tensor quantity. Okay. So that can be written as, because it is a tensor quantity, it will depend upon the two direction. Tau ij del I del j plus only the similar, like in the coordinate geometry, only the same direction will be added. Here again you have the only the similar unit vectors will be added to each other. The magnitude of the similar unit vectors can be added to each other. Okay, then again you have the sigma ij del I del j. You cannot use mn here. And if you use mn, you cannot add the both quantities. You can only add the both quantities when the unit vectors are same. Okay. Now you can write, you can add this, magnitude will be added together. Tau ij plus sigma ij. Similar to the vector quantities, here you have del I del j. This is the addition. Of two second order tensor quantities. Okay, then you have the subtraction. Okay, for subtraction again, similarly the vector quantity you can write subtract the two second order tensor quantities.
So is it like that the del has to be underlined like that?
Del has to be,
Underlined like
it is a vector quantity. Generally in the new books you will find that for any vector you have to make a put a line above it, and that means the vector. In this subject we will make the vector quantity, we write the vector quantity by using a line below the notation. Okay.
okay.
This represent, it is a vector. It is a unit vector. You know the definition of unit vector. What is the unit vector? Which has a one direction and unit
Magnitude
magnitude.
is one.
Magnitude is one. Okay, that is the unit vector. So tau minus sigma, that can be written as tau ij del I del j. These are the unit vectors minus, these are magnitude. Here tau ij and sigma ij are the magnitude. This is not the vector quantity. This is the magnitude, and this represents the vector. Sigma ij, sigma I, sigma j. Now, when you subtract this, you will get tau ij minus sigma ij. Magnitude will be subtracted together and multiply by del I del j. Okay. Now we will see the multiplication operation, which are more important. This is the addition subtraction, that is same as the vector quantity or the first order tensor quantities. Now we will see the multiplication of the second order tensor quantity. So first is a multiplication of a second order tensor quantity with a scalar quantity. Okay. Suppose A is a scalar quantity, tau is a second order tensor quantity. So you will get A multiplied by tau ij del I del j. The magnitude will be multiplied. So A multiplied by tau, that will be some number. Tau ij, that will be some number multiplied by del I del j. So it is again a second order tensor quantity. So multiplication of a second order tensor quantity with scalar quantity is a second order tensor quantity. Okay. Second is multiplication of a second order tensor quantity with a vector quantity. Okay. Multiplication of a second order tensor quantity with a vector quantity. Okay. So you can write, so there are three types of multiplication because there are three different operation occurs between the vector quantities. So first is the dyadic product. So again in second 2.1, that is the dyadic product. Of a vector and second order tensor. Okay. So suppose you want to take a dyadic product. Dyadic product means direct multiplication. You don't have any sign in between the two quantities. Tau is a second order tensor, V is a vector. So you can write tau ij multiplied by del I del j, then Vk multiplied by del k. So when you take the dyadic product, you have to multiply the magnitude and multiply the directions. Okay, so you have tau ij Vk del I del j and del k. So this is a third order tensor quantity. Here you have the three direction. This is a third order tensor quantity. So in natural world, there is a no physical quantity which present in the which has the three direction, because in the natural world in space you have only the three direction. You can have the quantity which depends upon the two direction. You can't have a quantity which depends upon the three direction in the three-dimensional space. You know, in hypothetical physics, you may assume in the quantum physics, like in the quantum physics, you may assume the 4 or 5 dimensional space, or you may assume the 11 dimensional space. There you may have the third order quantities, you know, the quantities, the properties which may depend upon, or the physical quantities which may depend upon the three directions. Okay, but in the real world, because in the chemical engineering we will only solve the problem of the real world, we will use the Newtonian physics, we will not use the quantum physics. Okay, in the Newtonian physics you have the three dimensions, and in the three-dimensional world the quantities may depend upon only the two directions. And it may depend upon the zero direction, it may not depend upon the direction, it may depend upon one direction, or it may depend upon two directions. So this you will not find this operation in real world. Okay, dyadic product of a tensor and vector quantity is not possible in the real world. Okay, second is dot product of a vector and second order tensor quantity. Dot product of a vector and second order tensor quantity. Okay, so you have tau, which is a second order tensor, dot v. V is a vector quantity. So you can write tau ij, this is a magnitude, multiplied by directions, unit vectors, del I del j, because it is a second order tensor quantity, dot Vk del k. Okay, now I have told you that whenever you have the dot operation between the more second order tensor quantities, you have to take the dot operation between the nearer vectors. Okay, so the dot operation will occur between the del j and del k. It may not, it cannot occur between the del I and del k, because nearer vectors are j and k only. Okay, so you can write magnitude will be multiplied tau ij dk, del I remain as it is, and then you have del j dot del k. So you will take the dot product between these two unit vectors, del j and del k. You will get tau ij dk, del I will remain as it is. Here you have conical delta jk. and this will equal to 1 when you have j equal to k. So I am replacing k to j. And you have both options. Either you can replace j to k or you can replace k to j. Okay, so I am replacing k to j. Okay, so you will get del ij bj del I. Okay, now here this is a first order tensor quantity or a vector quantity. This is a first order tensor quantity or a vector quantity. No, that means a vector quantity. So basically you will find this operation in the word because the vector quantities are present in the word. So you will find tau dot v in the several operations. Okay. In the equation of motion you will find tau dot v. Okay. Now the third operation which is possible is the cross product of a tensor and vector and second order tensor quantity. The third type of operation is cross product of a vector and a second order tensor quantity. So you have tau cross v. Okay. So write down it in the unit vector form. Tau ij del I del j cross vk del k. Again, you have to remember that the cross operation will occur between the nearer vectors. You cannot take the cross product between del I del k. Cross product will only occur between del j del k. Okay, the magnitude will be multiplied ij vk. These are the magnitude. Then you have del I that will remain as it is, and you have the cross product between del j cross del k. Now when you take the cross product between del j and del k, it will become alternating unit tensor. Ij vk del I, when you take the cross product, that will a alternating unit tensor will come. J k, here you have to introduce a new indices. That new indices represent the perpendicular direction of the surface which is made by the ij del j del k unit vectors. So here I am introducing new indices L, and then you have to multiply it by new unit vector del L. Okay, so your final value will be tau ij vk epsilon jkl. This is the magnitude, multiply by del I del L. So this is a second order tensor quantity. Okay, so you may find this type of quantities in the real world because second order tensor quantities are possible in the real world. Okay, now we will see the operation between the mathematical operation between the two second order tensors. Okay, the multiplication operation between the two second order tensors. So these are the example of multiplication of a tensor and a vector quantity. Okay, now we will see the multiplication of two second order tensor quantities. Okay, so first the dyadic product. So when you take the dyadic product of the two second order tensor quantity, you will end up with fourth order tensor quantity. Okay, so just I am solving this. So this will become tau ij del I del j sigma mn del m del n. So when you take the dyadic product, this will become tau ij sigma mn del I del j del m del n. So this is a fourth order tensor quantity. So you will not find this type of quantity in the real world. That's why you will not find the dyadic product of the two tensor quantity in the real operations. Okay. In the mathematics which you are going to use, you will not find this operation because it resulted as a fourth order tensor quantity, which is not possible. Okay. Similarly, the cross product, when you take the cross product, of two second order tensor quantities, so suppose you are taking the tau cross sigma. Okay, so that will be equal to tau ij del I del j cross sigma mn del m del n. Now the cross product will occurs between the nearer vectors, that is j and m. Okay, so you can take the cross product between the j and m only. So this will equivalent to tau ij, magnitude will be multiplied first, sigma mn, then you have to write the remaining vectors del I del n. These are the remaining unit vectors, and you have to take the cross product between del j cross del m, which are near to each other. Okay, now when you take the cross product, here you will get tau ij sigma mn. Here alternating unit tensor will come, that will be j m, and you have to introduce new indices l, and then you have the remaining unit vectors del I del n and del l. This is the new one which comes due to the cross product. Okay, so this is a third order tensor quantity. So this type of quantities are also not present in the real world. Okay, so you will not find you cannot use the cross product of the two second order tensor in the real world, and you will not find this type of problem where the you have to take the cross product of two second order tensor quantities. Okay. Now the third is dot product of two second order tensor quantity. This is possible in the real world. Dot product of two second order tensor quantities. Okay, so you have sigma dot tau or tau dot sigma. Okay, so you can write sigma I, sigma ij, del I, del j. These are the unit vectors. Dot tau mn, del m, del n. Now again you have to remember that the dot operation occurs between the nearer vectors. So nearer vectors are the j and m. So here the dot operation only occurs between j and m only. Okay. Now you can multiply the magnitude sigma ij tau mn, then write remaining vectors del I, del n. These are the remaining vectors. Then you have to take the dot product between sigma j dot sigma n. So when you take the dot product between these two quantities, it will convert it in the chronicle delta ij tau mn del I, del n chronicle delta. This is not a vector quantity, this is a magnitude. Chronicle delta is a magnitude. It has the value 1 or 0. Chronicle delta jm. So that equal to 1 when j equal to m. Okay. So here you either you have to replace m to j or j to m. So I am replacing m to j. So the quantity new quantity will be sigma ij tau jn multiply by sigma I, sigma n, del I, del n. So this is a second order tensor quantity. So this operation is possible between the two second order tensor quantities. So dot operation, you will find this operation in the real world. Okay, you will use this operation. These two operations you cannot use, because these are not possible in the real world. In real world, only the second order tensor quantity is possible. So you can use the dot product. You can take the dot product between the two second order tensor quantity. Now the fourth type of operation, which is called the possible multiplication operation, double dot product of the double dot product of the two second order tensor quantities. So this is new one. You will not find the double dot product between the two vector quantity. It is only possible in the second order tensor quantity. Okay. So double dot products are represented like this: tau double dot sigma. This double dot product is a special type of multiplication which only occurs when you have the second order tensor quantities. Okay, so you can write tau ij del I, del j double dot sigma mn del m del n. Now, in the double dot product, first you have to take the dot product between the nearer vectors, then you have to take the dot product between the farthest vectors. Okay, so in this case, you have to take the double dot between j and m, then you have to take the double dot between I and n. Okay, so you can write tau ij sigma mn. These are the magnitudes. Then first take the double dot between sigma j dot del j dot del m. Then take the double dot product between del I and del n. Okay. Now nearest vector and farthest vectors. Okay. Now that is equal to tau ij sigma mn. This will become chronicle delta jm, that is equal to 1 when you have j equal to m, and this will become chronicle delta in, and that is equal to 1 when you have I equal to n. Otherwise the values of chronicle deltas are 0, and if it is 0 then whole terms will become 0. So that will not written here. So you have to either replace j to m or j to n. Similarly, you have to either replace I to n or n to I. So here I am replacing m and n to I and j. So tau ij sigma, in place of m I am writing j, and in place of n I am writing I, sigma ji. So this is and there is no unit vectors remaining. So this is a scalar quantity. So double dot product of two second order tensor is a scalar quantity. Okay. So these are the main mathematical operations between the two second order tensor quantities, second order tensor and vector quantities, as well as vector and the scalar quantity. Now the del operations. Okay, so I will explain you the most important del operation. Only the one type of del operation present in the second order tensor quantity, that is the divergence of a second order tensor field. Because del operator is a vector quantity, so you only have the del operator is a vector quantity, multiplication of the vector and tensor, so you have the divergence dot product. Okay, divergence of a second order tensor field. That is del dot tau. Okay, so when you take divergence, you can write del I del by del xi dot tau mn. These are the unit vectors, del m del n. Okay, now just multiply the magnitude, you will get del tau mn divided by del xi. You have to take dot operation between the nearer vector, so I and m, and the del n remain as it is, and you have to take dot product between the nearest vectors. So you have del I dot del m. So when you take the dot product, it will become the chronicle delta. by del xi del n canonical delta in. Okay, and when you have the canonical delta, that is equal to 1 when I equal to m. So here I am replacing I to m. Okay, so you will get del tau mn divided by del xm del n. So this is a first order, this is the first order tensor quantity or a vector quantity. Curl of a second order tensor quantity is possible, but you will not find such operation in the transport phenomena. You may find this operation in the electrical engineering. In the electricity, you will find this operation, but in the transport phenomena, we don't have the curl of a second order tensor quantity.
Excuse me, sir.
Yes. Yes, yes. बोलो भाई.
Sir, if it's possible, then can we do the rest in the next class?
बस this part I will complete है ना, within 2 or 3 minutes I am completing the class है ना. So curl means del cross v, del cross tau है ना, curl of a second order tensor quantity. Del cross tau. So just write del I del by del xi cross tau mn del m del n. Now you have to take the cross product between nearest factors and multiply the magnitude. So you have tau mn divided by del xi, del n will remain as it is, and you have the cross product between del I cross del n. Okay, now when you take the cross product, you will get the epsilon sign tau mn divided by del xi multiply by magnitude. This is a magnitude, so I am writing before epsilon I m and mu indices L. Okay, and you have del n del n. Okay, so this is the second order tensor quantity. And because this is a second order tensor quantity, so the curl of the second order tensor is a second order tensor quantity. This operation is possible in the real world, but you will not find such an operation in transport phenomena. In heat transfer, mass transfer, in the fluid mechanics, you will not find such operation. You may find this operation in the other fields of engineering, like electrical engineering, okay, or the electronics. You will find this type of operation, but in the mass transfer, heat transfer, in fluid mechanics, you will not find this operation in a curl of a second order tensor field. Okay, this is all about the mathematical operation. In next class, we will solve some identity, we will prove some identity for the unit vectors and tensor, and from the next week we will start the actual mathematical part and the actual subject. ठीक है, और किसी कुछ पूछना है?
No, sir.
चलो, I will share the notes with you, है ना.